And today we are going to talk about Brownian motion, uh, which is probably the most important example of the use of time-dependent statistical mechanics. And today we'll talk about the formulation given by Albert Einstein in 1905. So it is about 116 years old formulation. So we'll talk about it today. So to begin with, uh, let me show you a slide. Can you see the slide?
Yes, sir.
Yeah. So what do I mean by Brownian motion? Brownian motion means you can think of this is a colloidal particle, the yellow one, and this colloidal particle is immersed in a fluid, could be water, and these black dots actually represent your water molecules or solvent molecules. So you can see that because it is at finite temperature, all these water molecules will move very fast. It has some translational motion, and it will bombard this much heavier and much bigger colloidal particle. So if I now ask you to follow the trajectory of these colloidal particle, you will see that the trajectory the shown in here is not deterministic. It is completely uh, random or zigzag. So what this colloidal particle executes is known as Brownian motion. And so if you are asked to write down the equation of motion, which we'll talk about it in the next class, not this class, at the single particle level, then you will see that you have to take care of the interaction of this colloidal particle with these water molecules or solvent molecules. And that is essentially uh, taken care by using a random noise in your equation of motion. So you can actually write down a Newton's equation with a random kick, and you will see that this random kick has some properties, and we will see that in the next class. And that description is called the Langevin description of that equation of motion is called Langevin equation. We'll talk about it later in the next class, but today we'll talk about another description where rather than thinking of a single particle, you can think of n number of particles, like here shown here, many particles. Each particle is executing Brownian motion. So you can think of a situation where each particle is executing Brownian motion, and then you're asked to write down the equation of motion, not for the particle, rather how the density of this particle change as a function of time and as a function of space. So basically, I can describe the system with the density is a function of time and space, and there will be a time evolution of this density, and that is given by what is known as Einstein's diffusion equation. So random walk at the single particle level leads to what is known as diffusion. For example, if I put a drop of ink in water, you know what happens if I put a drop of ink in water. You see that initially it is concentrated, then it's a blue ink, for example. It is initially concentrated at some point, and then it will disperse. These particles will start moving, and this movement is a part of this movement is due to Brownian motion. It will disperse. It will just this particle will move in all the possible direction. There is no preferred direction to go. It will move, and if I wait for a minute or two, if I come back, you will see that the color of water has become now light blue, and the density is uniform, so the particles are present everywhere. So ideally you should get a density profile at very short time, which is like a delta function, because it's concentrated, it's peaked at a position, and then this delta function kind of distribution will broaden and it will spread over all the space, and eventually in the very long time limit, which is basically in this case after a few minutes, if you come back and see what happened, that you'll see that density is uniform. So it will be so density will be like a flat line if I plot as a function of position, like a flat line. We'll talk about it. So we have to give a mathematical description, a theoretical description, and this is given by Einstein in 1905. But actually the first experiment was done by a botanist called Robert Brown in 1828. He had looked at this pollen grains in alcohol under the microscope, and he could see the motion shown something like here. This is a simulation, of course, the random motion of this pollen grain, and he thought that, okay, it's like 200 years old. So he thought that, okay, this motion are due to some molecule which is a primitive molecule, and he also saw this motion with some other substances. So he thought, okay, maybe this is the primitive molecule which is the source of life. So this is a living molecule, he thought, which is not true, because it was shown by pollen grains, which is a big particle, several micron, immersed in water or in alcohol. But what he looked at was this Brownian motion, the zigzag movement of this pollen grain. Okay, so with this, now I'll start. Uh, As usual, start with the description given by Einstein, which is in 1905. So Einstein wrote several papers in 1905, and one of these papers was on Brownian motion. Okay, so say for example, I have this is a number of particles I have. Small n is a number of particles. Okay, so I can think of that. Okay, I have n number of particles, say colloidal particle or pollen grain immersed in water. So this is small n is the number of colloidal particles, and each of these particles is executing this random motion, random kick, because of the random kick from the environment, from the water molecule, from the solvent molecule. And you can also always write, for example, if I say that dn, of course, dn is much smaller than n, is a fraction of molecule, of course. Dn by n is a fraction of molecule. Dn is okay. Is a number of molecules. This is also number of molecules, but rather particles, I call it, which experience a displacement between this is called delta and delta plus d of delta, okay, in time interval tau. For simplicity, assume one dimension. Okay, actually the motion is in 3D, but you will deal with one dimension. Okay, so for simplicity, take 1D motion. Now this time interval tau is very important. What is this time interval? Time interval tau is, sorry, is small compared to observation time. Okay, so this tau is small compared to observation time, but larger than any correlation time. What does it mean? Any? So for example, I observe this phenomena. I'm tracking this pollen grain for say 10 seconds. So that is my total observation time. And this tau is much smaller than 10 seconds, number one. But it has to be greater than if there is a correlation time in the problem, in the system. What do I mean? For example, if I have two events, if I have many particles, so I have one particle moving and another, many particles moving, even if I follow a single particle, its position at time t and the position at time say t plus some delta t, these two positions should be completely independent of each other. Okay, so if I have a position, if I know the particle position as xt and x t plus delta t, sorry, delta t, rather I use not delta t, my notation tau, t plus tau, then these two positions completely uncorrelated. So the position at x t plus tau has nothing to do with its previous position, its earlier position at x t. Okay, so they are completely uncorrelated. This is how one can think of. Uh, so if it is the case, uh, then I can always write, for example, that I can write this ratio dn by n. This is a dn is the number of particles which experience a displacement of delta, and displacement between delta and delta plus d delta in this time interval tau. So dn by n is the fraction, and this is equal to some function which I am calling function of this delta times the interval in space. Okay, okay, interval in space. So phi delta times d delta. Okay, so what is this phi delta? This phi delta is called the probability of jump. Now I'll talk about few properties of this phi delta function, not delta function, like this function phi, which is a function of delta. Delta is like dx, you understand? No? This is a displacement. It has a dimension of displacement. So phi delta multiplied by d delta, and if I integrate this, say for all possible values of delta. Now delta could be negative or positive. No, this is like a probability of jump. So this is a probability distribution in a way. So this should be conserved. No, this should be equal to 1. Okay, this is one property. What is another property? Another important property of this function is that this is, if I take this phi of delta minus delta, say, that must be equal to phi of delta, because I cannot say that probability of having jump with minus delta is different from probability of having a jump with plus delta, because the sign of delta should not matter, rather the magnitude of delta should matter. So this function should be a function of the magnitude of delta, not its sign. So what we are looking at, we are looking at a random walk of this particle, this tagged colloidal particle in one dimension, this Brownian motion of the random walk. Okay, so it can, if we start at the origin, for example, it can go to the left side, it can go to the right side. Okay, so whether it will go to the left side or right side, there is no preference. Okay, that's why any jump, whether it is on the towards the left or right, they are of equal probability if the jump distance is the same. So that's why this function has to be a function of delta in such a way that this is an even function. Is it clear to all of you? This is very,
Yes,
very
sir. Yes, sir.
even function. It cannot be, why? Because you are on a line, for example. You start here. You can jump in this direction, you can jump in this direction. So both the distance are, say, delta. Okay, this is your origin. So the jumping towards your right and jumping towards your left should be of equal probability as long as your jump lengths are the same. Is this clear? You're a random
Yes,
walker. No?
sir.
You can go to the right, you can go to the left. Does not matter you go to the left or right. Your probability of jump is same if you go the same distance. If I go 0.1 nanometer in the towards left or 0.1 towards right, both the events should have equal probability. That's why this probability function, the probability of jump, should be an even function of your jump displacement delta. Is this clear? Because this is what we are going to use in this uh, formula, in this formalism. So I can always define, for example, that okay, I can call nu, which is a function of x comma t. What is this? This is your number of particles per unit volume at time t. I can think of. Okay, and this is actually your probability distribution. So now let me draw a picture. Sorry, let me draw a picture better. Like this. Okay, so you start here and then you go like this. This is your random walk now. Okay, so this is at time t, and I call this position as x plus delta time t, and this is your position which is x, okay, at time t plus tau. So your initial position is x plus delta. I can always think this x plus delta, doesn't matter, and your final position is x. Okay, and your initial time is t and the final time is t plus tau. What do you mean by initial final? I mean any two events. I just take any two events. Is this clear? So I can always write down this, for example, that if I write down this, that this number of particles per unit volume at time t, rather at time t plus tau. So I can think this is the x, this is the position x at time t plus tau. But you had started where? You had started here. What was the probability? It was probability was f x plus delta. What was the time? Time was t. But then from here to here, you have gone through some jump process, no, with some probability phi of delta. So I should multiply with phi of delta, okay, in order to get the distribution at time t plus tau. Now, is it the complete story? Is it the complete story? Or maybe I should write something more. Can anyone comment? Is it the complete story, or I can say something more? People are there or not?
Yes, sir.
Is it the complete story, or I should add something to this? It is not the complete story because this is one of the events. But I did not say that what is the delta. Did I tell you what is the delta? I did
No,
not tell
sir.
you, no? I did not tell you, isn't it? I can
No.
have a situation that within that time period tau, same time period, not tau, yeah, tau, t plus tau minus t, which is tau. You can have another situation that a particle within the distance travels another, not delta, but delta 1 or delta 2. And it will come and add, isn't it? It's a probability distribution. Is this clear?
Yes, sir. So integrate over.
I should actually integrate over all possible values of delta, because delta is the jump within the time interval tau, but delta can vary. It could be from what to what? Tell me. Delta could be from minus infinity to plus infinity. So actually I should integrate this quantity. Is this clear? This is very important. Very, very important. What do you do? I know my particle position at x plus at time t is x plus delta, and then time t plus tau it is at x. Now I ask, what is the probability of finding the particle at time t plus tau, rather at time t plus tau with position x. Now you can think of a situation that the particle was at here at x plus delta at time t, and it jumps to this place. Okay, but again you think that this delta is not constant. Delta could be anything. No? I can think of a delta which is twice this delta. It can jump from here to here because they're moving randomly, no? But within the tau time period, it has jumped from that position to your final position. So if you calculate the distribution of or the number density of your particles at that point x at time t plus tau, it has to be sum over all possible events like this. This is summing over, isn't it? Integrating over delta d delta means you're summing over. You're assuming it is continuous. That's why you're integrating. You're integrating over all possible values of delta. So you are calculating distribution function at this point at some time, say t. You can have a situation the particle was here, it comes from here. This one trajectory. Another trajectory could be that it comes from somewhere else but comes here. All of them should add, and that give rise to your distribution. Is this clear, Anish and others? Because this is very important.
Yes.
Very important. Think of it has to be like this. It has to be like this. So this was the distribution here, and then multiplied with the jump. Okay, and then I integrate over all possible values of delta. It has to be, because if I keep like this, if I don't integrate, then this function should depend on delta. But on your left, you have something which is independent of delta. So I have to integrate over all delta. Is this clear? This quantity has nothing to do with delta. It is a function of position x and time t plus tau, but it is not a function of delta. So this is how it should be. Okay, so we'll write it down like this. So this is very important that you get it. Now what I do Taylor expansion here. If I do Taylor expansion of this quantity shown here, what I'm going to get here on the left hand side, this is Taylor expansion in time. Is this clear? I hope this is clear. And this is equal to, I have an integral like this. Now this function, I'm again doing some Taylor expansion. If I do Taylor expansion of this function, let me write down, put the curly bracket, f x comma t. What will be the next term? Plus
Delta del f del
Delta
x.
del f by del x.
delta del f del x plus okay, and I don't take after this. Whole thing is multiplied with phi delta d delta. So if I now explicitly write down the left hand side, I'll have three integrals. What are those integrals? Fine with all of you?
Yes, sir.
Now look at all these integral very carefully and try to get the physics. This integral. See, this f has nothing to do with delta. So essentially you have integration of this. This is the integral.
Yes, sir.
And if I integrate, what I'm going to get?
1.
It was
1.
1, no? So essentially I get f x comma t. What about the next term?
0.
Yeah, because you have integral like this. This is the integral. And this is 0. Why it is 0? Because it is actually you're calculating something like average of delta, but your f of delta is even function. So this even times or this odd function, the whole is odd function integrated in the symmetric um, interval. It has to be 0. The first moment is 0 delta, because it is equal probability to go to the right, equal probability of going to the left. So the on an average delta has to be 0. What about this quantity? What about this quantity? Tell me.
Non-zero.
It is non-zero. So let me write down it again. Uh, what I have my left hand side. Sorry, del f del t. Now I can cancel this too. Okay,
Yes, sir.
and then what I can write, what I'm going to get, I'm going to get something like del f is a function of x comma t into del t is equal to uh, delta square by 2 factorial into tau phi delta. Okay, this is exactly what I have. And I can see this is an integral. No? Essentially, you have to calculate this integral. This is an integral divided by 1 by 2 tau, 1 by 2 tau rather, isn't it? So this I'm calling it d, and I'm calling it diffusion coefficient. Okay. So what I have now, have you seen this equation before? This is called Einstein's diffusion equation. How many of you knew about it? At least knew about it. This is in 1D, of course. I have written in 1D. How many of you knew about it? Tell me. Anish, Pooja, Nashit,
No, sir.
No, sir.
did not know. That's
I have
strange.
seen this, but I once I knew.
Okay, so this is Einstein's famous equation, Einstein's diffusion equation. Okay, now I write down another equation. Or you know this equation?
Yes, sir.
So can I just write it like this? This is minus, okay, so actually you can call plus h cross by twice m into I. It has the same structure. This is for a free particle, no?
Yes, sir.
This is called Schrodinger equation. For a free particle. Same structure. Look at it, Anish.
Yes,
Mathematically
sir.
same.
Same wave equation.
Yes. It is, yeah, but it's not wave equation. Wave equation has second derivative in time, but Schrodinger equation. Okay.
Yes.
The same structure. How did you solve this equation, Schrodinger equation?
Separating time and space.
Yeah,
Forming.
because when you solve it, we took this as as boundary value problem. Remember? It's called
Yes.
boundary value problem. Solving it using separation of variable technique. So, remember this? Quantum mechanics, you go. But
Yes, sir.
this equation will not solve as a boundary value problem because this is not the physics. So this is something else. Because this equation has to be solved using some initial condition. And what is that called? If you make use of the initial condition to solve differential equation.
Initial value problem.
Yeah, so it should be solved using initial. It is essentially an initial value problem. What is the initial value problem here? If you solve Schrodinger this Einstein equation, what is the initial value? What is the condition? Condition
Initial
is
value.
that f at x at time 0, this must be equal to what? Something like n times delta function, because this is called Dirac delta function. We have talked about Dirac delta function, no? It is very important for this course. Why Dirac delta function? Because I said, because at time 0, if you put a drop of ink in water, it is concentrated at that position, isn't it? So you have a distribution which is very sharp at x0. So that is where I put my drop of ink. So very very sharp peak at that position, very high peak, and no no probability if I go away from that position. So it should be something like a Dirac delta function. Mathematically, it should be a Dirac delta function like this. Okay. So Dirac delta function, you know the properties of Dirac delta function that you have done, no?
Yes, sir.
How many of you know the properties of Dirac delta function?
Yes, sir. You had
Okay.
told also.
Yeah. So let me write down if x0 is n is the number of particles, no? Delta x, because if you integrate this, you should get total number of particles. That's why I put n. You can think of this problem also in terms of a single particle. Then I choose n to be 1. Then you are following one particle, but you're talking about its distribution of that one particle, single particle. The realization over many uh, uh, mm, you have to take average over many realization. Anyway, so the delta function property, you know that delta function, delta of x is 0. When is 0? When x is not equal to 0, but it goes to infinity. It is huge when x is 0, isn't it? So I told you that
Yes,
delta
sir.
function has meaning when it is inside an integral. That is when it is very useful, isn't it? We had used this kind of property of delta function, that f of x0 I think I use, yeah. You know this. This is a delta function property of a delta function. Is this clear?
Yes, sir.
Yeah.
Yes,
Yes,
sir.
sir.
Now today we'll make use of what is known as Fourier representation of delta function. So let us do it. This you should know. So this delta function can be expressed as an Fourier integral, as a Fourier integral, which is given by this expression. This is called Fourier representation of delta function. This is very important. Try to remember this. How many of you knew about it in some other context? BA students, you had seen this? Nashit,
Yes, sir. For it.
Manish. So this is called Fourier representation of a delta function. Okay, this is how it is. Okay, now you will make use of this. This is very important. So if it is Fourier representation of delta function, we'll be using it later. So let us write down this f xt. This can also I can express as a Fourier transform of another function. How do I write? It will 1/2 pi f tilde k comma t. It is equal of ikx dk. You understand this? So basically, I am representing this as the Fourier transform of f tilde k comma t. Is this clear? This should not be a problem, no? Because see, you integrate over k, so no k dependence on your left. And this is the definition of Fourier transformation. Okay, I cannot teach you the whole Fourier transformation in this course. No, you have to go and check some books. So this is how it is. Now let us. Now you remember what is your diffusion equation? No? This is the diffusion equation. So on your left, you have a time derivative of your function f of x comma t. So take a time derivative here. If I take a time derivative here, what I'm going to get? If I take a time derivative here, what I'm going to get? I'm going to get the time dependence is only here in f tilde k comma t. So I have to take a derivative of this quantity with respect to time. Is this clear? It's very simple thing.
Yes, sir.
And on the right hand side, what you had something like diffusion constant time, second derivative of f with respect to position x. So for the right hand side, I do d. I have to do this, which is equal to 1/2 pi into d. Now look at it. Where is x sitting? X sitting is here. Exponential of ikx, isn't it? Not in f tilde. So f tilde is unaltered. But if I take a derivative of this exponential of ikx twice with respect to x, what do I get?
Minus k square.
I get ik whole square, isn't it? Is this fine?
Yes, sir.
Yes, sir.
Okay. Now this is equal to dy 2 pi. You have a minus sign here, or I can put the plus sign here. Does not matter. Essentially, I have this, isn't it? Is this clear? Is this clear? Now compare. Any problem? Any problem?
No, sir.
I k whole square is I square is -1, no? That's why minus k square. Okay. Now compare 1 and 2, not 1 and 2, sorry, A and B. What do you see? See very carefully. If I compare one A and B, see, I know that this is equal to this, no?
First order differential equation time.
And I know this is equal to this, no? Because diffusion equation. Remember the diffusion equation is this, no? This is what you are solving, no? So this equal to is this. Look at the structure. 1 by 2 s will cancel anyway. But you have exponential ikx dx inside, and then so basically it tells you that this part has to be equal to, yeah, sorry, isn't it? Is this clear?
Yes, sir.
Is this clear to all of you? See, look at it. They must be equal to, they must be same, isn't it? Look at it. Twice pi, don't care. Exponential of ikx dk. So it gives you what? It gives you del f tilde kt dt is equal to minus dk square f tilde kt. So in the k space, k is the conjugate variable for x. It's like momentum. Okay. This is what you get. Any problem so far? Tell me. Very simple thing I'm doing. It's not so difficult, no? Because I compare these two, I see this part has to be equal to this, isn't it? Because both are Fourier transform.
Yes, sir.
Okay, this is how it is. Now, if I solve this equation, what I'm going to get? If I solve this equation, the equation, let me write down again. Del f tilde kt dt you can solve this equation, not very difficult to solve, no?
Yes.
What is the solution? Tell me.
F tilde k0 e to the minus dk square t.
This is how it is, isn't it? Is this clear?
Yes, sir.
Is this clear? Now what you had this. Recall. x0. What is this? N times delta x. This is the initial value problem, initial condition, no? This is what you had, isn't it? So I will make use of that. So let us do it. That also I know from the Fourier transformation that f of x comma 0. What will be the answer? It is 1 by twice pi. We're adding as a Fourier integral. Is this fine? Is this fine? Just I had the
Yes,
expression with time t. Now I replace t with 0. Is this fine? Should be fine, no? This should be fine. Let's look at carefully. If it is not fine, tell me. Go back. This is the expression, no? F of x comma t is 1 by twice pi f tilde k comma t. This. Exactly the same. Only just I replace t with 0 at time 0.
Yes, sir.
And also I can write this again as n. Now you know what is delta function? Delta function is 1 by twice pi. We had used, no, the Fourier representation of delta function. Now what does it tell? Again same comparison, no, comparing these two. What do you see? You see that this quantity, this f tilde k0, is equal to n, isn't it? Because they are equal. So this is equal, no? They are same. It gives you f tilde k0 is equal to n. Is this fine with all of you?
Yes,
Tell
sir.
me.
Yes, sir.
It's not a very difficult thing. So now what I have f tilde k comma t is equal to this. This is equal to n. I know n. This is fine. So my equation has become now simpler. Okay. So now what I need to know, I want to calculate what is f of x comma t. What is f of x comma t? Again I write down. It is a Fourier transformation, no? This is your definition, exactly the one I used here. Now this is going to be what? 1 by twice pi n e to the power of minus dk square t. This one gives you n by twice pi integral basically I am left with carrying out this integration, isn't it? If I
Yes,
can
sir.
carry out this integration, I know what is the distribution at time t at position x, isn't it? Now how many of you can carry out this integration? Any idea how to carry out this integration?
You can complete the square inside on
Yeah,
the
you're right.
exponent.
You're right. So let us complete the square inside. So what I can do, so actually you have actually why you have this, no, minus, if I take, I think I'll go to the next page. That's better. Whatever. Just a minute. I'll go to the next page rather because that is better. So what I have here is this. Uh, f of x comma t is n by twice pi integral This is exactly the expression, isn't it? So this one I can write it as n by twice pi. Let me do it here only. E to the power of minus. Okay. The first term is dk squared t. I can write it. I can actually write it like this: k root over dt whole square. This is the first term, no? Next term is plus. If I take a minus, it will be minus ikx. So basically, your a minus b whole square means a square minus 2ab plus b square. So minus 2ab equal to minus ikx, isn't it? So basically, it is 2a is this, but you have to make b so that you get ikx minus ikx. What should I do? I should divide by 2, isn't it? I should divide by 2. What should I do? I should multiply it by I x, and also I divided by root over dt. Is this clear? And then this is your b. So b square I should add. What is b square? Plus this. I square is minus 1. Is this clear? That it is minus 1.
Yes.
So actually you should write x square into I square, which I minus 1, divided by 4 dt. But if you have added this, you have to subtract the same thing, no? So actually you should have also exponential of minus x square by 4 dt. Is this clear? Essentially making the whole square. I'm just doing it in very detail. So what is this quantity? Exponential of minus. So this one is a minus b whole square. This is a minus b whole square, no? Whole square dk. Of course, this thing I can take it outside the integral. So I'll just write it like this. Fine? Fine with all of you?
Yes.
Is this fine? So now let y equals to then dy equals to what? Dy equals to
dk root dt.
dk root dt. And since this is the integral is from minus to plus infinity, does not matter the integration limit. Although I'm cheating a little bit here, but anyway, take it for granted. It is exponential of minus y square dk is dy divided by root over dt. Now you remember this expression? This is a standard integral, no? The standard integral,
Yes.
Gaussian integral. So you have the Gaussian integral here. So what I have here is n by twice pi e to the power of minus x square by 4 dt into 1 by root over dt, and this one will give me what? Root over pi, no? Isn't it? So what I get? I get n divided by root over 4 pi dt fine. This is the expression I get. Check, I think this is exactly what I get.
Yes, yes.
And this is your probability distribution for a particle executing random walk or Brownian motion without any external potential, free particle, but executing random walk. And this you obtain by solving this probability distribution, no? Probability density. Solving the diffusion equation due to Einstein. Now, in many cases, you see that people take n equals to 1 here. They are dealing with a single tack particle. For n equals to 1, what will be the value? This f of x comma t. And this is the value, not the value, rather expression is widely used in the literature. It's for a free diffusion. How many have you seen this? People from my group must have seen, but I don't know about others. I'm not sure about others. And this is so beautiful, isn't it? Now, if you plot this, how does it going to look like? Tell me. What you can see, it is Gaussian in position, isn't it? Of course, the width depends on time. The width of the Gaussian depends on time. It is linear in time, but in Gaussian in position. So let me try to show you something here. Can everyone see this? So this is distribution. So what do you think? Again, you see, think about the experiment. Put a glass of water, take a glass of water, put a drop of ink. It is highly dense at time 0. When you put it, and as time progresses, it will diffuse all the ink particles, and eventually it will be uniform density. It's a time dependent density kind of thing. No, it is a delta function. Then it will broaden, 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 and it will be flat like this. And this is exactly what you get. This is the expression what you get by solving the diffusion equation due to Einstein. This one. And if I plot this as a function of time, it would look something like this. So if I
Hello, sir.
yeah
Sir, taking n is equal to 1, that is single particle. How
yeah
can we physically explain this diffusion thing?
very easy. Single particle means, actually, see, even if you have a single particle, you can think of a distribution of a single particle, no?
So at suppose at t is equal to infinite. So in case of multiple particle, it becomes a constant. The density becomes constant.
No, if it
Okay.
is multiple particle, then if you integrate the density, that will give you total number of particles, which is n. If it is single particle, if you integrate the density over space, it will give you 1. There are two description. One is single particle description, another one is n particle description.
Mhm.
I can, in this room I have gas molecules. No, I can always think of n particle distribution, and I can also tag one of the gas molecule. I can think of its distribution, isn't it?
Yes, sir.
That's how it is, essentially, nothing else. So basically, if I plot this distribution, this is exactly when you start. It's like a delta function. Okay, at time 0 or very short time. As the time progresses, it will become what? It will become broaden. Can you see this? You can see, you know, the one I'm showing the animation. Can you see, all of you, the animation?
Yes.
Yes,
So you drop of ink in water. The distribution is like a delta function. Then it broadens and broadens, and then it will be flat. I do not show this to be flat because I did not run it for long enough time. If I run it for long enough time, then you can see that it will be really, really flat. Can you see that it is flattening? Like, it doesn't show because the axis shifts, but essentially it flattens. It goes like this. Is this clear to all of you? Physically, physics is very important.
Yes, sir.
You should not forget this in your life. A drop of ink in water. How the density change as a function of time, like from a delta function to Gaussian, to broad Gaussian, broader Gaussian, and then eventually it will be, the distribution will be what? It will be
Constant.
parallel to x-axis, isn't it? Unbound. Now I can think of that I have three particles with different diffusion constant. I did not talk much about the diffusion constant, which I will do in the next class maybe. But I can always think of three particles, so red, yellow, and blue, with three diffusion constant. Now, diffusion constant, in my definition, what is the diffusion constant? Look at it. Where did I define? Here. This is my diffusion constant, no? So what is this? Something like average square of the displacement.
Yes, sir.
This is the average square of the displacement, no? This is called mean square displacement. But you have to divide by some time. Tau is time. 2 times that time. So your diffusion constant or diffusion coefficient is something like mean square displacement in 1D divided by 2 times time. MSD, mean square displacement, MSD by 2t or 2 tau, whatever the notation is. Okay. So now it is obvious that the particle which will move more, which will have higher mean square displacement, will have higher diffusion constant, isn't it?
Yes, sir.
So the particle which is
Yes.
moving faster or which is moving more will have higher diffusion constant. In the Langevin description, in the next class, we will see how that diffusion constant depend on particle size, temperature, and viscosity of the medium. There is a relation called Stokes-Simson relation, which tells you that your diffusion constant D is equal to kVt divided by 6 pi eta r. Eta is the viscosity, r is the radius of the particle for a spherical particle. Okay, so it is proportional to temperature and inversely proportional to the viscosity of the medium. Okay, so now coming back to this, so if I have three particles with three diffusion constant or diffusion coefficient, also called diffusivity, then the one which has a higher diffusivity, what do you expect? Higher diffusivity means the particle will travel more distances, isn't it? You travel more distance. It will have higher mean square displacements, higher diffusion constant. So now tell me which one should have a broader distribution at times at any time. One is with lower diffusivity, lower diffusion constant. Other one with higher diffusion constant. Tell me.
The spread will be greater.
Higher would be for greater spread.
Higher will be greater spread, because if you see the expression also, because this your spread is proportional to diffusion constant, the width of the distribution. So the one which has higher diffusion constant will have higher, bigger width. And as a result, if I show you this picture, and then I show you this animation. Now tell me which one has a higher diffusion constant, the blue, yellow, and the green. Sorry,
Green one.
saffron and the green. Which one has a higher diffusion constant?
Green.
Green one has a higher diffusion constant. Are you sure? It is. But you see that it is the area under the curve is conserved. So if you have higher width, the height decreases, isn't it? If you integrate this over space, it should be equal to 1. That you can go and check that your distribution is normalized. Is this clear so far what I have discussed?
Yes.
Yes, sir.
Okay, now next, if I calculate average displacement, average x, what will be the value? This is my expression. Average x, this is the distribution given to you. You know statistical mechanics, how to calculate. Now here the distribution, it depends on time. That's why it is time dependent statistical mechanics. So earlier you are dealing with time independent distributions. Here we are dealing with time dependent distribution. So now tell me, what is average x?
0.
It will be 0, because it is even function of x, exponential minus x square Gaussian. So multiply with x, integrate from minus infinity plus infinity, it will give you 0. So average displacement is 0, obvious, because it has equal probability of going to the left or going to the right, isn't it? So the average displacement should be 0. But what about average x square? Will it be 0 or not?
Non-zero.
No, it won't be zero.
But average x cube?
Again 0.
0
0.
again.
So all the odd moments are 0, and all the even moments are non-zero.
Non-zero.
Is it clear to all of you?
Yes, sir.
So this is your expression. So let me work in one particle description, single particle description. Sorry. Sometimes I have problem writing because I write too many equations sometimes, and it is too much of load. Even for the PowerPoint, they don't like it seems. Okay. There's a time lag. Just wait for a minute. Meanwhile, if you have a question, you can ask. But you never forget a drop of ink in water. Huh? Delta function Gaussian, then it will spread like this.
Hello, sir.
If I don't have a potential, if I have a potential, it's a harmonic oscillator, what will happen? Will it keep on spreading at time infinity, goes to infinity?
No, sir.
It will actually attain a Boltzmann distribution. Harmonic is half kx square, no? So in the long time limit, your distribution will like exponential of minus beta h. H is your half kx square. So beta k x square by 2. Exponential of minus beta k x square by 2. Yeah, somebody has a question.
Sir,
Ask.
in this treatment, where did we actually use this the condition that we imposed on tau? Like,
No, this is underlying. Underlying. So yeah, we have imposed one condition, of course, because when you write like this, no,
Mhm.
so this equation assume that you have this underlying assumption that tau is like that. It is not too short. So
And
in other words, the dynamics Markovian.
another thing, we in the Taylor expansion,
Yes,
we the t is expanded up to like order 1 and x is expanded up to order 2.
yes, yes.
So is it for a particular reason that we use this?
I don't know, because if you can include the second t square kind of a thing, but this is going to be very, very small. I think that what happens that time is very tiny. So tau square is so small that you can neglect. But here, this one you should not neglect, because it is a fast non-zero term in your expansion, no? Fast non-zero term. Other than this, you should not neglect this. So you truncate here, and on the other left hand side you truncate to linear in t, linear in time. You can go up to t square, t cube, but these are negligibly small, so you can just ignore. Okay.
Yes.
This is the treatment of Einstein. Exactly, I'm teaching this from Einstein's paper. This is how exactly it is done. You guys should go and check Einstein's paper. Google it, or I can send it later. Okay, so what are the expression for this f of x comma t? I had expression like okay. This is the expression. Now I ask you to calculate this x square average. How do you calculate? Because you see that x average is 0. All the odd moments are 0. And all the even moments are non-zero. Okay, so all the odd moments are 0, all the even moments are non-zero. So let us calculate x square average. Dx, huh? So you have to calculate this integral. How do you calculate? Kailash Shahu, you remember this calculation?
No, sir.
Okay. So the integral,
The
I know this
first
one. Alpha x square dx. I give you this integral. You know what is the answer to this?
root pi by alpha.
Standard integral. Now if I take this integral and I just differentiate with respect to alpha, what I'm going to get? I'm going to get minus isn't it? Because your x square will come down, no, from exponential, and with minus alpha, minus x square, so minus is outside, and this is equal to minus, you know, nx to the power n minus 1. If you do carefully, you'll see this is nothing but, because if you differentiate this with respect to alpha, to differentiate this with respect to alpha, you get this. Differentiate this integral with respect to alpha, you get this. So they are equal. Okay, with a minus sign, of course. They are equal. So it essentially tells you that your x square this one equal to, is this clear? Is this clear to all of you? It's very, very simple thing what I did. This is an integral. This is a standard integral. If I integrate this, sorry, if I differentiate this integral with respect to alpha, I'll get what? I'll get exponential minus alpha x square times minus x square. No, that's why I put minus outside. This is how it is. Similarly, I differentiate this with respect to alpha, I get this, and they are equal. So it basically means my x square into this is given by this. Essentially, this is the expression for second moment. So I can make use of this integral. Anish, can you tell me what should I write here?
Substituting alpha as 1 by
So alpha is what? Here alpha is here
1 by 4 dt.
So alpha is 1 over 4 dt. So it should be 1 by 2 alpha, which is, sorry, I have to wait. One by 4 dt. Now pi by alpha means pi divided by 1 by 4 dt whole to the power of half. Look at very carefully what I have. I have 1 by root over 4 pi dt. Now this one will give me what? 1 by 2 dt, which is 1 over 1 by 2 dt, which is 2 dt, no? And this one give me what? This is nothing but, again you look at it, 4 pi dt, isn't it? So this will cancel. And what do you get after cancellation? Get your x square average is equal to, and this is very important result what you have derived today. This is mean square displacement, isn't it? It is linear
Time.
in time, and it is larger if your diffusion constant is higher. Is this clear? This is very important result. But if it is like this, I can always calculate this what is known as square root of this, which is going to be like 2d. Is this clear? This is the mean displacement rather.
Yes, sir.
This is mean displacement. But if I have a Newtonian particle moving with constant velocity, what is the mean displacement? No random kick from the solvent. Tell me. Moving with constant velocity.
Square of 10.
Huh?
Should go a square of 10.
Lambda x is going to be what? You know,
Proportional to
volume, sorry, velocity times time. It is Vt, no?
Yes.
It is not root over t, it is linear in t. And your displacement square will be t square. That is called ballistic. So if you have lambda x square, in this case it will be like t square, and this is called ballistic motion. If you have a Newtonian particle moving with constant velocity, but if it is diffusive, then your mean square displacement is linear in time. That is, this is called diffusive. So this is the difference between diffusive and ballistic motion. Okay, we'll stop here today. I think it is too much. If I progress further, it will be too much. Okay. So we'll meet not on Monday. Monday is holy. I think it is holy. It's a holiday. Don't play holy, but it's a holiday. So the next class is on next Thursday, which is on which is 1st of April Fool. Anyway, okay. So we'll have it on that Thursday. We'll do a little bit here, and we'll go to Langeva description. Okay.
Okay.
I hope you have followed today's class.
Yes, sir.
Yes, sir.
Very important, because it is from the original Einstein's paper. I'm telling you, Einstein derivation was almost like this. Then I have my own way of doing things, of course. Okay, so thank you very much. I'll upload this, and then I'll upload the video.
Thank you.
Thank you very much for your patience.
Thank you, sir.
Yes.
Thank you, sir.